Hello everyone, welcome back to our Calculus 3, Chapter 15. And today I'm going to cover two sections, 15.4 and 15.5. We'll be talking about some applications of double integrals that you guys learned on the previous three sections of the course. So let's start with the section 15.4 first. I'm going to talking about some applications in physics. Okay, so first we talk about something called centroid, or centroid, that was density, centroid, center of mass, right? Center of mass. So pretty much the idea is you have a plate, because lamina or something, plates, okay? Imagine that this has no thickness, it only have area, okay? So center of mass is the point where, so if I call it, this is what? X-axis, this is the y-axis, okay? Center of mass is going to be denoted by x bar, comma y bar. It's a point somewhere, may or may not be on the plates, such that, say, for example, imagine this is, let me choose an easy, a lighter book, okay? You'll find a point, such that your whole book can be balanced on that point. I gotta find a point. And this point called the center of mass. Another thing that we learned in Calc 2 already. The difference is in Calc 2, they give you a very nice case as well. The density is constant. Density, I spelled it right. Density denoted by rho is a constant. However, in Calc 3, we're going to make the problem a little bit more complicated. In this case, density may not be a constant. Means what? At some part of the plate is going to be heavier than the other part. More particles going to concentrate on one part compared to the others. Who knows? Okay. So density may not be a constant. Okay, but the idea is going to be the same. You want to calculate the centroid. We're going to learn something called the moment and the mass. Okay, so how do you calculate the mass? First of all, it's out of ink. So let me choose a better marker. Black one. Mass. In physics, mass is calculated by density. Density. This is my E. City times the. So now it's going to be two-dimensional, okay? No thickness, so just time the area. If you have a 3D, usually in real life you have a 3D object, then you take density times what? The volume, okay? So you have the mass. It's the same idea, but one more dimension. So in here we only talk about two-dimensional object, which is not happening in real life. Everything in real life is going to be three-dimensional space. But imagine that the plates is going to be very, very skinny, very thin, so no thickness in here. We only have two dimensions, x and y. That's it. So density times the area. Okay? The thing is, density now is a function in terms of x, y. Means what? Density at that point right there may not be the same as the density as the point right there. Means what? The materials was not equally distributed. Okay? And some part would be lighter, would be less particle concentrated than the other. Okay? And then the idea to calculate the mass of the whole object is, let's denote by little m. For mass of the whole object is what? Rho xy times dA, and then integral. dA means what? You calculate the area of a little pit. Okay? And then you time the density at that point. Density times little area, you have a little mass. Okay? And you add all little mass together. I should write double integral. And then let's call that region R again. Okay? That's going to be the mass of the whole object. And let's call these objects R, like what we did on the previous three sections. Okay? So I can write this way if you like to. The total mass is the sum of all the little mass over the entire region R. Okay? dm means a little bit of the mass. Okay? Which is rho times dA. Again, rho is the density at that point, and time dA is a little area. Density times area is a little mass, and then you add all little mass. So this is two variable x, y, so double integral over the region R. Okay. And if you use rectangular coordinates, it's going to be dx, dy, or dy dx. And if you use polar coordinates, it's going to be what? R dr d theta. Actually, there's a formula to interchange the variable between x and y and r and theta, whatever. Maybe 2, maybe 3, maybe more than 2, 3 variables. let's go look for this word if you want, Jacobian. Okay, I think it's in 15.9 or something. We're not gonna cover in the course, but I may show you this later on when we talk about three-dimensional space triple integral. And you see, we can always change from one set of variables into another set of variables using something called Jacobian. But just two variables is easy for now, so just write down dx, dy is equal to r, dr, d theta. This is for polar, rectangle coordinate, x, y, change to polar, r and theta. This is your formula for now, okay? And of course, x is r cosine theta and y is r sine theta. We just mentioned that. Now, in here, this is the mass, okay? You have the mass of the whole object calculated this way. This is the formula for the mass. And now I'm going to talk about something called moment. Moment. I think our book denoted by a capital M. Mass is lowercase m, okay? Moment is upper M is what? The distance times the mass, or mass times the distance. Let's write the whole thing down, make it clear. Moment is equal to mass times distance. So this is the idea. This is a value to tell you what? Okay, let me show you the book. This is a book, my pre-calculus book, okay? It has some mass in here. So if my origin if I carry the book with my hand straight like this, so the distance from the book into my body is longer, I feel it's heavier, and it's harder for me to carry the book. Okay, but if I move the book this way, then well, what? It's the same mass, but the distance from the book to my body is closer, and then it's easier for me to carry. And that point is called moment. Mass times the distance. Okay. Okay, so you want to calculate the center of mass right here. It just means what? You want to calculate the moments, and you divide it by the mass of the objects. You're going to have the center of mass. Okay, so in here we have two dimensions, so we have to calculate 2 times x and y, x, y, and y bar. So first of all, the moment with respect to the x-axis. Okay, so the x-axis is right here, and think of I'm standing on the x-axis, and this is my book right here. So the distance from me to my book is that much. This is the center in average. Okay, I'm calculating my distance, my moment with respect to the x-axis. So me is right here, x-axis, and the book is right here. Okay, so mx is equal to, again, mass times distance, and the distance from x-axis to the object is going to be y. You see, it's y, right? And then the mass, the distance is y already. The mass is rho times g. I'm sorry, rho times area. So the area. So this is the distance, and this is the mass, and this is the distance right here. Okay, distance times the mass. Okay, and this is distance times the mass of a little bit of the thing, a little box right here. You're going to add them all together. You have the moment for the whole thing. Okay, double integral over the region A. Okay, and then you can calculate y bar. Okay, y bar is mx over the little m. This is moment with respect to the x-axis. Okay, so this is y bar. Calculate the moment of the whole thing divided by the mass of the whole thing. Because in average, what? Mass time distance is the moment, right? Because you have this. Moment is equal to mass times the distance. And you want to calculate the distance. And the average, the whole thing right here, the center is at this point, y bar is what? Mass times distance, moment. So distance is moment divided by mass. And similarly, you can calculate the my. I need some room to write. Right, so big right here. So my is now you're standing right here. You're right here. Okay, and your book is right here, and this is gonna be x bar. Okay. Very similar to this formula right here. Double integral. I better write here. Double integral over the region R. Now it's x times rho xy dA. Okay. Every little box right here, the mass is rho times dA, and then the distance to your pivot is x. Okay, and then you take this, you multiply this and by the mass, you have moment of that little bit, and you add them up, you have the moment of the whole thing. And then after having the moment, you can calculate x bar is same formula right here is what? My over m. And x bar, y bar will be your center of mass. Okay. If mass is, if density is a constant, rho is a constant, then what? You can pull out that rho outside the integral, so you come back to calc 2. Okay? But here, the difference is what? Rho may not be constant. You have to include rho inside of the integral, and rho is a function in terms of two variables. That's why we write x, y, and you have to use double integral to calculate. And this is a formula that you need to calculate the centroid. That's just the word we use. Some people use called the center of mass. This is the point of balance. Okay, with the points in here, it's going to be balanced. Okay, let's move on. Another example, another application. Let's see what they call moment of inertia. I don't know how to explain it. Let's say it this way. This is like the resistance of an object due to the movement or velocity, right? So what? You look at the people who do skating, so it's called skater, right? So if she or he want to spin fast, see what they do? They try to move the hand close to the body, then they can spin real fast. What if they move the hand that way, and what happened? They tend to move slower. In other words, if the mass spread out farther away from the center of spinning axis, okay, then the moment of inertia denoted by letter I is going to be bigger. Bigger I means what? Bigger resistance, so you got to move slower. Smaller I means what? Smaller of resistance, then you guys tend to move faster. So if you want to have a smaller I, you try to move all the mass close to the spinning axis, okay? And if you want to spread it out, the mass is far away from the spinning axis, then the inertia, moment of inertia, are going to be bigger. It's going to slow you down. Okay, so the formula for I in physics is, I think, it's mass. Let's just write m as mass times the radius squared, the distance squared. Okay, mr squared. It's inertia. The moment of inertia is going to be mr squared, where m stands for the mass of the object and r or d is stands for the distance. Yeah. Okay. And again here, say you have an object. Okay, this is x-axis, this is y-axis. You want to calculate the inertia around the x-axis, so denoted by ix. It's going to be what? Double integral of y square rho xy dA region R. One more time, you recognize that quantity right here. Rho, this A stands for what? Area, right? Rho times the area is going to be what? The little mass, and then y square right here is the distance square. We talk about x, right? So this is the axis rotating, x-axis, and that object's rotating around the x-axis. We talked about the inertia around the x-axis, ix, right? Similarly, IY, now you're right here, object rotating about the y-axis, okay, is double integral. The distance from the object to the y-axis is gonna be x squared rho xy dA over the region R. Okay. And again, if the object is further, then inertia is gonna be bigger. And in other words, R is bigger, then I is bigger, R is smaller. Let's square up, okay? And same for M, it's not square in here. You have a bigger mass farther away, then I is gonna be bigger. And then I see another applications in this section 15.4. They talk about probability. Say probability when x is somewhere between A to B. This is single variable calculus. Cal 1 is integral from A to B f of x dx. This is the what? Probability function, okay? And run from A to B. And anyone who took statistics, you know, we have something called normal curve. Okay, this is a function f x. Let me look for a function. For the bell shape, the bell curve, I think the function looks like this. 1 over, look it up, sigma square root of 2 pi e to the x minus mu square, I think, or negative x minus mu square over 2 sigma square. Sigma here is standard deviation for the population, and mu here is the population mean. Okay, you don't need to know that this is a function anyway, one variable. And in statistics, you have the three magic number, empirical number, they call it 68, 95, 99.7, I think. So you integrate this one standard deviation, 2 standard deviation, 3 standard deviation, and probability if 1 standard deviation away from the center is 60% chance, and then 2 standard deviation is going to be 95% chance, and 3 standard deviation is going to be 99.7% chance. Anyway, this is just count 1, 1, and this is probability when you have something between A and B in general. You do integral. Okay. And same thing for 2D. Well, think of, instead of having the bell-shaped curve this way, you have the bell-shaped curve like 2D. Okay, and you have probability for x is between A to B, and y is between C to D. That's going to be double integral function f xy dx dy, x run from A to B and y run from C to D. And probability for something that fall into the region when x run from A to B and y run from C to D. Okay, it's just an interpretation of double integral problem that you may see in statistics or in physics like previous example. And that's just all I think. Let me see if I missed something on 15.4 before I move on. They have something called the expected value, is the mean, okay? And I'm not sure, I don't remember I give you any homework on this, but I see that work in the book, so I'll just show it to you. Expected value. So you can think of this one, this is the mean. Okay? In other words, you say this, in the long run, what will happen to the whole event if keep doing all the time? So in other words, you're a gambler, right? You're assuming, okay? You're a gambler, you go to the casino, you ask yourself, what if I keep continuously keep gambling all the time? What will be the final outcome? What is the expected value? Of course, the answer is what? We're going to lose money, okay? Because, you know what? The casino is going to always have the positive expected value on their side. They hire a lot of PhD people to calculate for them, so they always have a better chance to win. So in average, some people may win occasionally, but ultimately, if people keep playing all the time, then what? The casino is always the winner. Okay. And well, I forgot. forgot to show you a formula for this expected value. It's a mean, which is integral from negative infinity to positive infinity of x, fx, dx for one variable. And you have mu1 or mu2 for, okay? So x, right, is called a mu1. And then expected value for y is called mu2. Same thing. So integral from negative infinity to positive infinity. Okay. Oh, so two variables are going to be f, xy, dA. The first formula was in one variable, so we have to adjust a little to two variables. Then y, fxy, dA. Okay. I don't think I give you any exercise in this, but since when they show you some examples on this, I think it's worth to know just for your information. This is called what? The x mean, this is called the y mean, okay? The mean respect to x, the mean respect to y. That's it. And then I'm gonna move on to 15.5. I'll talk about the very last section for this clip, talk about surface area. Surface area. Okay. Let's recall in count one. We have something called the arc length. Arc length. So say you have a function. You want to calculate the arc length. It's just like a little curve on that function. You have a formula in count one. So the arc length is integral from a to b, square root of 1 plus f prime square or dy over dx square dx, right? So function is f of x, y equals f of x. And the idea is this, you kind of cut it up into very small pieces, right? This is called ds. ds is what? Changes of dx, this changes of dy. So Pythagorean theorem, ds square equal to dx square plus dy square. Okay. dy square or ds equal to square root of dx square plus dy square, or you can factor the dx square root dx square 1 plus dy square over dx square, and then this is square root of 1 plus dy over dx square dx. This is pretty much the idea. Now you have the formula. Okay, this is the arc length a little bit, and you add all the little bit of the arc length together. You have the arc length for the entire curve from A to B. This is the formula. What's the idea? Okay, now we move on to count 3. We'll be talking about not the arc length anymore, two dimension, right? We talk about the surface area. Okay, so the idea in count 3 is this. I'm going to erase this, okay? Say you have surface, and the equation with this one is z is equal to f xy, right? We're talking about count 3 now. And you want to calculate the surface area of the region. X running from, say, A to B, and Y from C to D, for example. And how do you do that? Let me just throw out the formula. I think the book just threw out the formula. And after threw out the formula, I'll explain to you. The surface area is double integral square root of 1 plus fx squared plus fy squared dA, okay, over the region R. Okay, so I think it's better to explain to you using vector. I don't think the book showed it to you. Do it this way. Think of any point on the surface is a vector with x, comma, y, comma, f, right? F stands for z, fxy. Okay, this is vector R. And this is the vector formula for that surface area. At any point of x, y, you have a point on the surface. So remember something called the derivative, or partial derivative, Rx. Partial derivative in terms of x is going to be what? 1, comma 0, comma fx, right? Derivative of x with respect to x is 1, derivatives with y with respect to x is 0, okay? And then for f is fx, and then ry is 0, 1, fy. I think this is off the book, but I try to explain the formula to you instead of just give you one. All right, and say you want to calculate the little surface area right here. This is Ry, change in terms of y. This is Rx, okay, change of x. Okay. Now, what if you cross the two tangent vector right there, Rx and Ry? Rx cross Ry, and if you learned before this, take the magnitude of it. It's gonna be the area for that little bit. Okay. So, what we're gonna do right here, we do the cross product too. So what? I, j, k. You cross this, right? For the I term is what? 0, fx, right? And then for the j term is what? 1 here and 0. So fy negative, and then for the k term is gonna be 1. So you have then square root because the magnitude. So square root of, I'll get to this. I'll get this side down. Right here. Rx cross Ry cross product, and then we find the magnitude is going to be square root of 1 plus fx squared plus fy squared. Okay? And this is the area of that little bit, and you add all of those, you have the formula right here. 1 fx squared fy squared. Okay. This should be dx dy. That was the idea. And I see that the book only took the formula to you, pretty much. Oh yeah, they got the explanation using delta, which is good, yes. Same thing in here. Okay, so let me wrap up this video clip today by showing you an example of how to calculate the surface area. It is simple for the formula, but be very careful when you do the math. As I say, in the integral, you have what? Square root, and then partial derivative in terms of x, partial derivative in terms of y. That means that there'll be a lot of algebra to take care of. And one more time, this is mathematics. You mess up with one number, you mess up with the whole problem. So be very careful. Okay, show you an example. I have one on top of my head for now, so let's show you. How about this? Z equal to 9 minus x squared plus y squared. What I'm thinking in my mind is this. This is upside down parabola. Okay. Okay. This is my z-axis, my y-axis right here. My z-axis right here. And my x-axis is right here. And you know what? Intersect, this is step 3. This is the bottom. This is 3. This is 3. We have, imagine this is upside up problem. And this is 9 right here. Okay. So, calculate the surface of the portion of surface of the parabola that is above the xy plane and up to is equal to 9, okay? The portion that's above the xy plane. Okay. So the projection now, the region that we're talking about is the circle, and the xy plane is going to be a circle of radius 3. So the surface area of that parabola is going to be double integral over the region R. In this case, that region is what? X squared plus y squared is equal to 9. Right? Circle right here where z equals 0. X squared plus y squared equals to 9. That function f x y dA. Oh, not this one. I'm sorry. Square root of 1 plus fx squared plus fy squared dA. That was the surface area one. Okay, so you have to calculate fx, fy, and this is your fxy. Okay? Z equal to fxy equal to 9 minus x squared minus 9 y squared. See what? I distributed the negative sign to the two terms. I have this. So fx is negative 2x and fy is negative 2y. So this is what? Double integral square root of 1 plus 4x squared plus 4y squared dx dy. You guys see why I have plus sign here even though I got negative 2x?